This is your lecture number 8. Today's discussion is about timers and counters. In this lecture, these topics will be covered: the introduction to the timers and counters, and their modes of operations, and the registers that we are using in AVR microcontrollers to set up the timers and counters, and finally a few example codes written in NetMLSTU. Okay, right. So timers and counters in AVR microcontrollers. So we have first of all, I would like to say what is a timer is. Time is something you count, like for example now, like a AVR microcontroller. So you have your CPU, right? And it has an internal or external oscillator. Let's say this is oscillator. So it generates a fixed frequency. If it is a 1 megahertz clock source available to CPU, right? So this clock pulse, it takes like a 1 microsecond to for one complete clock cycle, right? For here to here. So now, so we can use to count some time. For example, now the timers in AVR microcontrollers comes in 8-bit and 16-bit. If I take this to a 8-bit one, so this is bit number 0 and 1, 2, up to 7. So from this CPU clock, you can take this clock pulse and assign it to, because the timers is a separate hardware. It is inside the AVR, but it is a separate hardware, like a dedicated hardware for that. So it needs a clock source to generate this pulse, right? So whenever, if you can use this oscillator frequency available to the CPU, so for every clock cycle, you can update this 8-bit register. Like if this is for here, it will count as 1. Update this one, and in the next cycle, 2 pulses count, so the number will be 1 and 0. Likewise, like clock pulses goes 1, 2, 3, 4, and 5, like over the time. So it will update this register. And that is how we use the internal timer. For example, now I want to, I have like a sensor, or let's say like I have a LED bulb, right? So I want to turn this on every 1 second. I want to turn this on and off, like blink this LED. Normally, what we did earlier was using a delay function. So we use a delay function. So the CPU has to be busy and without doing anything, right? So I mean, when you go to this delay function, whatever the delay that you assign, the CPU comes to this function and it will stay here. And in your program, after executing, when it meets a delay function, so it will rotate in here, like it's like a small while loop, right? So if it is like a 1 second delay, so it will not do any other work. Like there are some other codes in the bottom. It won't go there. It will stay here without doing anything, right? But sometimes we don't want the CPU to just be busy here. There are some other sensors and everything connected to the microcontroller, maybe sensor 1 and sensor 2. Sometimes these guys need some service, right? So the CPU sometimes miss these events in communicating to these guys, because it's just being busy inside this delay function. So it is not doing anything and just being busy until this time duration ends. Okay, so that's one disadvantage of using a delay function. instead of that, we can blink this LED by using a timer. Timer means like you set this timer to, okay, I want every 1 second's time, give me a signal like when this is ready, right? So every time this timer will work like every 1 second, it will give a signal to the CPU, okay, it is a 1 second time. And in the next cycle, it again say to the CPU, okay, the next 1 second time. So you can write your code, the CPU knows like it's a 1 second and blink this LED and come back to its work, like this is your main program. And when CPU receives some kind of a signal from here for 1 second, so it will go and execute some kind of like a command here, and it will go back to your other work, right? Again, it's like an interrupt. So you are doing in the main function. So when the timer wakes you up the CPU, so it will go to interrupt service routine, different function, and do some work and return back to where it was, not like being busy in a delay function. So it is a one single advantage of using timers. And sometimes you can use to time, for example, now time between some kind of events. You can count the time, and so that's the advantage of using timers. There is a 8-bit timer, so that's what I have. So it can count up to 255. But if you want to count up to 16-bit to this value, 65,535, you can use a 16-bit timer. But most cases, the 8-bit timer will be okay. And so the thing is, like, you can use this timer as a counter as well, right? Operation is either this timer as a counter. Count is some the application will be, you are not using this clock pulse, right? So without using the CPU oscillator clock frequency, you can there is some pins for for input to this timer, right? So if you take this pin one, the counter pin, for example, now we have some sort of encoder, right? Like encoder is generating this kind of pulse for motor application. So the motor is rotating, so the encoder's pulses will be like that. So in order to like go one revolution, like for this motor, let's say it takes 10 pulses, right? 10 pulses. So you can couple this encoder to this pin. So each and every pulse, so it will update this the counter register, right? So when 10 pulses go, so you know this value is now updated to 10. So you know it's like a one revolution. If it is 5, you know like it's a half of revolution. If it is 20, you know like the motor has rotated 20 two revolutions. Okay. Or sometimes like applications, if you're using IR sensors or some kind of, let's say you have a supermarket, right? So this is the entrance. So you set like a IR sensor. So if a person enters through this IR sensor, so it will generate a pulse, and so you can give that pulse to this pin, and now the counter can be updated. So number of people entered to this supermarket can be counted using this one, right? Either you can use this external pin to produce this pulse, and then you can increment this register, or else you can use it, that is the counter. That's how you use it as a counter. If you want to use it as a timer, you know, like the CPU clock frequency. So every each and every pulse, you update this one, then you can measure this time if you know the value, right? So let's say like it's a 1 microsecond pulse. So if 10 pulses goes there, you know like the time is now 10 microseconds, right? So if 100 pulses goes from this CPU clock, it is 100 microseconds. And now this the CPU clock might be too fast. sometimes you don't need like this 255. You can count up to 255 microseconds if you use the 1 megahertz CPU clock frequency. Then your solution will be like a 255 microsecond, but that is too small. If you want to have a longer period, so you can use this pre-scales like 8, 64, 255, and 1024. For example, now if you use 8, which means for if the CPU clock pulses 8 clock pulses goes there, then only it will update this by 1, right? For 8 CPU clock pulses, it will update the counter by 1, right? Earlier, if you use no pre-scale, so it will, for every 1 pulse, it will update this one. But if you don't need that kind of like a fast operation, you can use some pre-scales, which means like divisions of the clock pulse, CPU clock pulses. You can update the timer in a slow manner, right? So that's all about the timers and counters. The applications, either you can use it as a timer, either you can use it as a counter. So like I mentioned, the timers and counters need a clock, right? It needs a clock, some kind of clock pulse. It can be counts in the internal using the CPU clock pulse, and it is pre-scales. While you can use it as an external pulse coming from a sensor or any kind of encoder, and you can use it as the whatever the pulse comes from the external source. It has a rising edge and it has a falling edge. You can set this register to be updated either using in rising edge or in the falling edge. But if you use the external clock sources, you can't use it, the pre-scales, right? So each and every clock pulse, it will be updated, no pre-scales, like you're using internal timer, internal clock of the microcontroller. Right, so the purposes are the use of timers and counters. The first one is you can use it as a counter. Count specific transition of external signal applied to the timer input pins, which means like there's an input pin for the microcontroller for timer. If you use the timers, T0 timer, so there's a pin for that. So you couple your whatever the signal coming from my external source to here. And the other way is to measure the time periods. If you know this, if you use your CPU clock period, so you know the CPU frequency. So if you know this register value, you know what is the how much time it has elapsed, right? So it doesn't need to start from 0. For example, now if the current timer value is, let's say, 10, right? So you read this one, you read it as 10, and after after spending some time, you will come back and see now the time is reached 110. So you know, like time between whatever the event is like 100 pulses, or the 100 bits here, right? So if you know the CPU or the clock frequency available to your timer, you can calculate the time period between these two events. The first, where you access this timer, and that was 10, and then when you come, it was 110. So the difference is 100. So you know, you can calculate the time duration if you know the frequency. If you know this time between one pulse, it is 1 microsecond if you use without any free scale. So you know it is 100 microsecond. So that's how you count the time between two events. And also you can use it to generate time periods, like I mentioned. you can blink a LED in 1 microsecond or 1 millisecond, any time period. So you can use timers to generate interrupts, and so you can generate time periods. That's what is told here, generate interrupts. And sometimes you can generate PWM waveforms. PWM is like pulse width modulation. So in order in motor controls, to change the speed, so we can generate some kind of if this motor works with let's say 5 volt. So if you put 5 volt, the motor will run in the maximum speed, right? And if you provide 2.5 volt, the motor will run at the half of the speed. But in microcontroller, it is hard to generate this kind of voltage levels. Either you have to use a digital to analog converter. Without using that, you can generate a PWM signal to this motor. If your PWM signal is like this, every time it is 5 volt, the motor will run like this. If it is half, I mean like you provide this kind of square wave signal, and this period and this periods are equal, so the average value will be this is 5 volt again, right? Average will be 2.5. Sometimes you can generate like a very small duty ratios, like this will be like a very small, so the average will be very low, like it could be 1 volt. Likewise, in order to change the voltage, you can change this turn on period. So that is what you call the PWM. That is what we're using in motor controllers. So in order to generate these PWM signals, you need to have the timers in the microcontroller. Right. So your timers and the counters can be in the microcontroller used in these 4 different modes. The first one is the normal mode, and the other one is clear timer on compare match, CTC mode, and fast PWM mode. PWM is used in motor controller as a way of fast PWM mode, and another one is phase correct PWM mode. So let's take a look at each one of these and see how we can configure the microcontroller to achieve these modes of operations. The simplest mode is the normal mode. So that is where you just use the timer or the counter to increment. I mean, for each and every clock period, whether it is internal or external. For rising edge or falling edge, you will set the timer to increment, right? Timer value, the register value, 8-bit register to increment, starting from 0 and updating it. So as you know, the timer simply overruns when it passes this maximum value. So the maximum value is 255. So if these pulses are 255, so the timer will be all this will be ones, right? So in the next pulse, after having this is filled to 255, in the next pulse, so you have 255 pulses has gone now. The next one, 256 one. So there's no any space in this 8-bit, right? There's no 9-bit. So what the timer can do is it can just reset. I mean, it's starting again from 0, right? So we call it as overflow. The timer is now overflow. So the timer can say to the CPU, okay, I'm overflow by enabling this overflow flag. So that is where this becomes 0. So it will say now it has overflow. So that's how you can, if you want to count more than 255, you can make an interrupt and push that value to another variable and count it as a 1. So likewise, you can use this overflow flag for different applications, but make sure the thing you need to understand, if it reaches 255, next cycle there won't be 256 because it's 8-bit. So it can just it's not going backwards. So what it does is just restart and set this timer to all zeros and count in again from 1, right? So it's timer reset. At the same time, if you enable the interrupts to generate the overflow flag, so it can generate the interrupt to say, okay, now I have reached 255. Then in the 256 cycle, it will generate the interrupt and saying the timer has overflown, right? So it just restarted. So this is the basics that you need to understand here. And there are some registers in the microcontroller. So if you search, these are the registers that we have to work to use the timers. The first one is TCCR0A, timer counter control register A. So if you just search from the data sheet of Atmega 328P, I have uploaded that data sheet to the LMS. You can download it. If you search this term, so it will go to this the timers and counters page. So you can locate this register. So it has a 8-bit. So different bits has a different configurations. Now this is where you use this CMO0A1 and CMO0AU. Those are used for other applications. So if you are using in the normal mode, by default everything is 0. So you are using it in the normal mode, right? You don't need to worry about anything. So TCCROA, initially all the things are 0. So which means it is on normal mode, right? You are not setting any bits there. So in the normal mode, WGMMO0 should be 0, and WGMO01 should be 0, and WGM02 should be 0. That's WGMO2 is not in this register, but it is in the other register, TCCR0B register. So it's a third bit, that is WGMO02. Again, that should be always 0. So in normal mode, you know, like every bit is 0. If you want to set this timer to normal mode, everything will be zeros, which means by default it comes in zeros. So you don't need to worry about setting anything. And CMO01 and CMO00 should be 0, right? And but you can use this timer prescalers in the control B register, that is CS00, CS01, and CS02. If you set them by default 0, no clock source counter timer stop, right? And if you use the 0001, you are using no prescaling, which means whatever the there's a CPU has a clock source, right? So your timer is here. So that timer will no prescaling means the same clock frequency. If it is 1 megahertz, 1 megahertz will be passed to your timer, right? No prescaling. So you have to set this on 0, 0, 1 if you want to use the same CPU clock frequency to your timer. If you need to slow it down to 8, I mean, like when there are 8 pulses let's say 1, 2, 3, 4, 5, 6, 7, and 8. So when there are 8 pulses pass, then your timer will be uploaded with 1 pulse, which is known as like a pre-scale of 8. I mean, like you have 8 pulses passes in your CPU, then your timer will be uploaded once. So it takes like 8 microseconds to upload your timer. So it's like a slow operation, right? So it's like a 8 pulses of the CPU needs to update the timer by 1. And if you use 64, it takes 64 pulses to update your timer by 1. So that's how you use it. Pre-scale if you want, doesn't need that kind of fast operation. And whatever the timer value is written in here, like so the timer register, this one will be uploaded to the clock available to the your timer. So each clock period, whether it's pre-scaled or not, so it will, for every rising edge, it will be updated this 8-bit register. Okay, so each and every pulse, this will be uploaded. So you can read this one. If you read, and if you know this value, so you know the elapsed time, like you know the available clock frequency, and you know this value, so you know how many pulses are there, then you can calculate the time. Right. And if you want to generate an interrupt, like I mentioned, in the event of overflow, so if the time is like maximum value 255, if it reaches 256, you can generate like an overflow flag. This is like a TOV0, which is the timer counter overflow flag. You know, like after the maximum value of the time is 255. So in the next clock cycle, it won't go to 256, right? It will go back to 0. So, but it will generate like a overflow flag. This set this bit to 1, and saying to your microcontroller, okay, so the timer has now overflown. So it is just reset. And so in order to enable this, you have to set this interrupt mask register TIMSK, and you have to set this bit to high. Then you will set this interrupts enable. Then only this will generate like an overflow flag within this interrupt event. So in most cases, we don't deal with this interrupt service routine for overflow. This is the example number 1. Here you have to write a program using Atmega 328P AVR microcontroller and using the internal 8 MHz oscillator to toggle a pin at RB01. This is the pin, and you have to toggle this pin with the period of 261 milliseconds using the normal mode of TIMR0 time. So if you are familiar with the Atmel Studio programming, this could be done very easily using a delay with 261 milliseconds, but now you need to do it by manually using the timer 01 interrupts. Right. So one important thing you need to note here that, so even though you have 8 MHz oscillator, internal oscillator, the CPU clock will be 1 MHz. This is how the fuse bits are set in this device by the manufacturer when it is shipped from the company. So the CPU speed will be 1 MHz. So there are some methods to change the CPU speed from the manufacturer defined value, but that is not covered in this lecture. So you have to assume that the CPU available speed is 1 megahertz, even though the internal oscillator is 8 megahertz. So these are the things that you need to note here. And your delay period should be 261 milliseconds, and your timer interrupt should be in normal mode. So this is the code. So the available CPU clock frequency is 1 megahertz. Since we are using the 8 megahertz internal oscillator, due to this field speeds, and the device is shipped to achieve 1 megahertz frequency available to your CPU. And since we are using the interrupt service routine, we have to enable the interrupt. So we are using the overflow, which means when the timer is overflown, it generates this, it will set the speed to high. So you have to enable this interrupt service routine by setting this one. When it is overflown, this bit will be set to high, right? So since you are using interrupts, you have to include this interrupt service header library. And this PB1 pin, this is that one, right? PB1. If you want to toggle means like you change the state from high to low, right? High to low. So if it was low, then you will change it to high. And if it is high, then you change it to low. If it is low, again, you change it to high. So this is that command to toggle this pin, right? So you can see this is bit number 1, PB1, and you set it to 1, right? And use this command. So then it will toggle this pin, high to low and low to high, right? And okay, so now as you know, we are using port B. This is port B, right? So the data direction DDR-B should be high. So I have set the whole port B to high, right? Either you can use only this pin, but I have set the whole port B. And initially I have turned it off. Initial, this one will be 0. And I want to use in the normal mode. Like I mentioned, if you use in the normal mode, TCCR0A should be all zeros, right? This is TCCR0A. Initially it is 0 because if you want to run it in the normal mode, WGMO01 and WMG00 in normal mode should be 0. And these two should be 0. And we are not using this one. So everything should be 0. You can skip this command. By default, it is 0, right? But it's better to tell the compiler set it all 0. And TCCR0B, I'm using the pre-scale of 1024 and in the normal mode, right? So the pre-scale, if I want to use 1024, it should be 101 in TCCR0B. So it is 101 here. This should be 1, and this should be 0, and this should be 1. See, 1024 pre-scaler. It should be 101 in TCCR0B. This is that, right? Which means you know, like the normal clock frequency is 1 megahertz. So which means it takes 1 microsecond to update the CPU, but now your pre-scale is 1024. So which means you take 1024 microseconds to update your timer by 1, right? So after reaching 1024 pulses of your CPU clock, the timer will be updated by 1. So which means in every 1024 microseconds, the CPU, the timer 0 will be updated by 1. And so we have to enable the interrupts. So we have to set, if you want to enable the interrupts, the TIMSK0 should be set for interrupt service routine. Now we can go and see this is that interrupt service routine. So TIMSK0, this TOIE0, this is that one, timer counter 0, overflow interrupt enable. So I have set this to high, so which means it generates an interrupt when it is overflow. Okay, so that is set, which means, and also if you look at the previous interrupts, external interrupt lecture, you will see that we have to enable the global interrupts if you want to enable any kind of interrupts. So you have to say, when you use this function, so global interrupts are enabled, which means you are telling the CPUs to enable all the interrupts, then only you can enable this interrupt. So the thing is that, so each and every 1,000 microseconds, so it will, like this is a 8-bit register, timer 0. So the timer 0 value is written to this register, right? TCNT0. Okay, right. So now we know that the CPU speed is 1 megahertz, which has a periodic time of 1 microsecond. So CPU in every CPU runs with 1 microseconds delay. So the timer prescale is 1024, which means it takes 1024 microsecond cycles to update the timer by 1. So which means that your timer is much slower than the operating speed of the CPU. So after passing 1024 of pulses, the timer will be updated by 1. Right? So the updated timer is value will be written to TCNT0 register. So that is an 8-bit register. The maximum value will be 255. So for the first 1024 microseconds, the TCNT0 will be updated to 1. So if there are another 1024 microseconds passes, so this will be updated to 2. Likewise, it will take 255 times to complete this process and generate the interrupt. So once the TCNT0 value become 255, so an interrupt will be generated. So now we can calculate the time that it takes to overflow this 8-bit register. So the maximum value is 255. In order to update this timer by 1 for 1 value, it takes 1024 microseconds. So 1024 into 255 is approximately equal to 261 milliseconds. So after 261 milliseconds, so the TCNT0 will be that will generate the interrupt. So the interrupt service routine will be executed, and the TCNT0 is the register will be reset to 0 again, so in order to count it again back from the 0. So once the interrupt service routine is executed, it will execute this line that is on the single line command pin change. So pin change is defined as the toggle the pin at port P0. So if the value was 0, it will be toggle to 1. If the value is 1, it will be toggle to 0. Likewise, the pin state will be changed for every interrupt service routine. Right now, so then, so that is interrupt service routine. Other than that, this is the main function. So when the function is started, it will do this initial setup, and then it will go to the while one loop. So the program will be looping on this while one loop until the timer interrupt is generated. So the timer interrupt function will be this. So the RP0 pin will be like this. So initially it was 0. Once this TC and T0 overflown and interrupt is generated, so that port pin state from 0 to 1, it will be changed to from 0 to 1. So it will be in this state, the logic 1 state, until the next time interrupt is generated, which means it takes 255 cycles, which is approximately 261 milliseconds to be in this state. After that, it will again, the state of the pin will be drops to 0. Likewise, it will resume from toggle the pin at each state. So this periodic time of this RB0 pin is 261 milliseconds. The turn on time is 361 milliseconds, and the turn off time will be the same. You can do anything here, right? So whenever the interrupts is generated, then only you go there and do this work, because it is just like a simple single line command. If you use a delay to do this, you are just being busy in this delay function without doing anything. Like you are not going to execute the other bottom lines, right? But here you can do any other work. But when there's an interrupt is generated, only you go there and do this work, right? So it is more beneficial to use timers without using these delay functions if you want to generate some time windows. All right. So now we are moving to the clear timer on compare match CTC mode. So that is something like you have the timer. This is your 8-bit CNT 0. This is your timer register. This one, TCNT 0. So 8-bit TCNT 0 timer register is this one. And you have another register called OCROA. It's also again 8-bit one. All right, so it's a 8-bit. The thing is that for OCROA, you can assign a pre-value. Like when you're writing your code, you can set this value to, let's say, any value. Like I can set this register value to, let's say, 120. Okay. So now this value is updated to 120. So this is your timer. So the timer will be updated by any clock period, whether it is pre-scaled or not. So you can generate, like in the previously we have generated interrupt service routine when this timer overflow, like when it is goes to 255. But here, you know, like this timer will be updated by each clock period, and when this is reaches to 120, so it is comparing with this OCROA register. It has a value 120, and now your TC and T0 has also goes to 120. When these values are matched, the timer will be your timer will be reset to 0, and also generate some kind of a interrupt. Okay, so it is used to compare like a specific time. So you know, like a 120 pulses elapse, and then you know it is the right time. But in the normal mode, we have just used overflow. We can just use only the 255. But here you can use any value between from 0 to 255. You can even set it to 50 or 26 or like a 33. So if you preset it to 33, when you clock this timer value reaches to 33, it will generate interrupt and reset. And the frequency of this generation, the waveform, if you want to generate a waveform, this is given by this one. This is available CPU clock frequency, and this is the pre-scaler value, and divide by 1 plus OCROA. So this is the OCROA value. I don't know why this where this one came, and divide by 2. So this, I'll take a look at example, how to use this capture compare CTC mode on, right? So this is the capture compare and how it works. So your TCNT, the timer will be counting, right? Starting from 0, it will counting. And once it reaches the value of the OCROA, the preset value of the other register, then the counter, now it is counting, let's say like OCROA is written to 35, right? So your TCNT, the timer 0 is like counting for every clock pulse, and it is updating its value like 1, 2, 3, 4 like that. When it goes to 35, it is compared with OCRO, so the values are equal, so the timer will be reset to 0, right? Reset to 0, and again starting from 0 and go counting up, and when it is go to 35, again reset to 0, right? So if it is like 100, so it will go to 100 and reset. And thing is like you can use it to generate a waveform. So there's a pin called OCN, right? That is this pin. OCOA pin, right? This one, pin number 12. So the pin number 12, OC, what is that? OC0A. Right. So initially OC0A is 0. The voltage is 0. So when it reaches to that 35 value, the comparison of OCROA, the timer will be reset to 0. At the same time, the OCROA pin will be set to high, right? And again, it is set to high. And then it is, the time is updating, and when it goes to there, then the OCROA pin will be reset. It is like a toggling the pin, right? So by using this one, you can generate like a square wave waveform with different duty ratio for PWM applications. So let's take a look at an example case. So if you want to use the CTC mode, these are the registers that you want to use. So compare output mode, non-PW mode, that is what you call CTC. So if you want to use this OCOA pin in the toggle mode, so you have to set this to 0 and 1, then you can toggle that. If you want to clear this pin, so you have to use 1 and 0. If you want to set that pin any event, so you have to set this to 1 and 1. So in normal operation, you are using them to 0. Okay. So this is the settings of TCR0 register. And other one is the in table 15.8. So CTC mode, WGM motive should be 0, and WGM 0, 1 and 0, 0 should be 1 and 0. So this should be 1 and 0, right? For if we want to use CTC mode. So we are dealing CTC0A mode. So here you need to assign the TCCR0 register. If you want to toggle that pin, so you have to use this one to 0 and this one to high. And these two bits should be set to 1 and 0. It should be set to 1 and 0. And you can in TCCR0 OB register, WGM mode 2, we have seen it should be set to 0 for CTC mode, so it is set to 0. And you can select any clock prescale, right? So 1024, if you want to use 1024, it is 101, and likewise. And this is the timer, the value of the timer is written in here. And this is your OCRO compare register, the value, the pre-assigned value, you have to write it here. And so this is, you have to now, you are not enabling this overflow. Instead, you are enabling this capture compare timer counter 0 output compare match interrupt enable. So you have to set the interrupt so OCIE or A, right? Not the overflow. In TIMS case 0 for to generate interrupts at each compare match. And when the compare match happens, so it will set this flag of the IFRO 0 register. Okay, so let's take a look at of this example number 2. This is a problem. Write a program for ATmega 328PA. We are using internal megahertz oscillator to toggle RB0 pin in every second using TIMERO timer in CTC mode, right? Previously we have used the normal mode. Now we are using the CTC mode. So the code will be the same. All the things will be the same. We are using this toggle in RP. And so this is your main function. So you go to the main function initial and goes to the setup. In the setups, these things will be set. I have using an additional counter variable, so you can use even your name like A, B, C, or any value. So counter value will be set to 0. My variable integer, it is initial 0. And I have to enable this CTC mode. So if I want to enable the CTC mode, TCCRO register, I have to go there. This is that one. So you know, for capture compare, so it will be I want to toggle that pin, so it should be 1 0 toggle, so 0 1, and let's say I'm using that one. Yeah, I'm not using the toggle pin because I'm just using port B, right? So I don't want to use that dedicated pin. I'm not using this dedicated pin, right? I'm using a different pin. So I'm not worried about using this toggling of this pin, right? I'm just using them 0. But I have to set this to capture compare CTC. So it should be 1 and 0 here, right? So TCCR0A should be 1 and 0 if I want to use CTC mode. You can see this should be 1 and 0. So I have done that one, right? Then I have to go to TCCR0OB for prescale. So I'm using prescale of 8, which means for every 8 clock passes of the CPU, I am updating my timer by 1. So if I want to use a prescale of 8, so it should be 0, 1, 0 written into these 3 bits. So it is 0, 1, 0. And my OCROA register predefined value is 100. So that is this OCRO output compare A register. So this is the value you have to assign initially to this register. So I'm using it as 100. And I have to enable the CTC mode interrupt. So TIMSK0. I have to go there and have to enable this timer counter 0 output compare match A interrupt enable and this bit, right? TIMSK0. Okay, so and then I have to call the global interrupts on. So then all are set. Now the prescale is 8, which means it takes 8 microseconds to update your ECN E0 register by 1, right? It takes 8 microseconds, which means like 0.008 milliseconds to update your TCTN, the timer register by 1. So you know this is 1, and I have this OCRO register 0A, which is set to 100. So it takes 100. So this TCNT0 has to count to up to 100 in order to reach this value, predefined value in this register, right? Then it will generate this interrupt. So 100 of this 8 microseconds is nearly 0.8 milliseconds. Okay, so that is not even close to a 1 second. So that's why I have used this counter variable. So every time when this reaches to 100, so there's a timer 0 compare A vector. It is not the overflow. If you compare this previous interrupt service routines, previous code, we have used this timer 0 overflow vector. Now we are using timer 0 compare A vector, right? Because we are using the timers to generate a compare. Previously, we are using the overflow. So that's why we're using this vector. So if you are not familiar with what are these vectors are, just go and look the previous lecture about the external interrupts. You will see why we are using this one, right? So we have to call this correct interrupt service routine. Then only you can work this function. So every 0.8 milliseconds, once it reaches to 100, it will generate an interrupt. Then I will update my counter variable by 1, right? So that is not even close to 1 millisecond. So I have to go 1025, which means like 0.8 milliseconds into 1250 is approximately 1 second, right? That's why I have used an additional counter. So once it reaches this one, the count is updated by 1. Again, the TC and T0 will be set to reset, and it is updating. And when it reaches to 100, generate again interrupt and update this counter, and again generating interrupt, updates this counter. And when the counter reaches to 1025, that is equals to 1 second, then I will call this pin change. So it will change the voltage level of the port P. And same time, I will reset this counter variable to 0 and starting the things from the beginning. So that's how you're using the CTC mode in to generate this kind of time periods. So the third example is write a program using ATmega 328P with internal 8 MHz oscillator to toggle the OC0 pin 50 microsecond on and 100 50 microseconds off. Now I'm not using this one, right? RB1. Instead, I'm using this dedicated OC0A register. So I want to generate like a PWM signal, 50 microseconds on and 150 microseconds off. And again, 50 microseconds on, 150 microseconds off. Likewise, I'm generating this kind of square wave signal using CTC mode. Okay. So now this the code will be the same, but instead I am using the toggle of OC0A pin in the compare mesh mode. So in that case, TCCR0A register, this one, right? So if you want to toggle that pin, set toggle OC0A on compare mesh, you have to set this bit to 0 and this bit to high, right? Then only you can toggle this pin on a compare mesh. Toggle this pin on compare mesh, so you have to assign that value, right? And I'm not using any pre-scale, so I have to set it to 1, right? If you set to 0, it won't work, right? No clock source. I have to set it to 1, so which means like each and every 1 microsecond, because my frequency of the CPU is 1 megahertz, which is 1 microsecond for each clock pulse. And OCR register, I use it to 50, and I have to enable this compare mesh in TMISK0 and enable the global interrupts. So this is my main function. So I initially do this setup and I wait for a while loop and doing anything. Then whenever this interrupt is generating on compare mesh on, so the timer, now this timer TCNT0 is updating like every 1 microsecond, it is updating by 1, right? 2, 3, like that, right? So when it reaches to 100, which is the value that you assign in OC, when it reaches to 50, because you have written 50 to this comparison register, so it will generate an interrupt, that is TMIRO compare A vector. It's the interrupt service routine. So I have using a variable called T flag. Either you can use it as like an integer or anything. In order to save the memory, I have using a char. It's like a 255 maximum. I just need to like use a value here, right? 1 or 0. Initially, I have set it to 1. So when there's an interrupt happens, which means like the timer value is now reaches to 50 of 1 microsecond period, interrupt is generated. So T flag initial value is 1. So this is true. If T flag is true, OCRO register is 150. So I can now update it to 150. This I'm changing it. Initially it was to initially it was 50. Now it is I'm updating it to 150, and I set this T flag to 0 and return, right? So what it does mean, so you know, initially it takes 50 cycles, right? Just give